Okay, so I checked 5 and 6, and the math was good on both of them, so we're going to leave it alone. We're going to move on to 7. And we're going to try. Okay, so let's go over here and get rid of all of this gobbledygook. And now we're going to look at 7. And 7 says, a young man accumulates a charge of Q1 positive 2 times 10 to the minus 5. Coulomb. While sliding out the front seat of a car, his girlfriend, who had been waiting in the wind, has picked up some extra electrons and now has a charge of negative 8. Draw a sketch of the situation. You know I can't draw, so we're going to say boy, and this is going to be girl. They're separated by a distance of 6 meters. But they're boyfriend and girlfriend. That's about 18 feet. Oh, that's pretty far. Want to find the force. 9 times 10 to the 9th. And 2 times 10 to the minus 5. Coulomb. 8 times 10 to the minus 5. And notice I'm not putting the signs of the charges in my equation. I'll deal with that when I talk about whether they're attractive or repulsive. So I got the force when I did it to be 0.4 newtons. And I said they were attractive because E was positive and Q was negative. Okay. So that was number 7. Number 8 says, suppose the two people in the previous problem move toward each other. Calculate the magnitude of electrical force of one on the other when their separation is reduced by a factor of 10. So now instead of being 6 meters apart, they're going to be 0.6 meters apart. So since should be able to do it a couple of ways. I should be able to say 9 times 10 to the 9th Newton meter squared over Coulomb squared times 2 times 10 to the minus 5 times 8 times 10 to the minus 5 all over 0.6 meters squared. Or what I said was, okay, 0.40 newtons. And then my value went from 6 meters down to a tenth of that, and a tenth squared is 100. So they should be 100 times more attracted to each other, and so 0.4 times 100 is 40 newtons. And that's my new force, and it's still an attractive force. Now, if what I'm saying to you is the truth, then I should be able to do the calculations of the equation to get the exact same thing. So if I turn on my calculator and look at, I have 9 times 2 times 8. And so on the top I have 144 times 10 to the negative 1. And then I want to divide that by 0.6 squared. And I get 40. What do you know? Math works. Physics works. Okay. So there's number 8. Let's scoot on to number 9. Number 9 says, two pit balls shown in the diagram below have a mass of 1 gram each and equal charges. One pit ball is suspended by an insulating thread. The other charge is brought to within 3 centimeters of the suspended ball. The suspended pit ball is deflected from its rest position until the thread makes an angle of 30 degrees with the vertical. At this angle, the ball is equilibrium. So then they, of course, want us to draw a force diagram. That's pretty easy to do. So here's my pit ball. It has gravity pulling down on it. It has an electric force acting on it that's pushing it to the right because the two balls have the same sign of charge. There's a tension in the y direction, and there's a tension in the x direction. And I know that Tx, since it's in equilibrium, has to equal the electric force. And then I know that Ty up has to equal mg down. And they want me to find mg for part, so there's my free body diagram, that's part A, and there's the tension. Part B says find the mg. Well, mg, they tell you that it has a mass of 1 gram, so it's 0.001 kilograms. Gravity is 9.8. So when I did that, I got 0.0098, 0.0098 newtons for B. And then C said, find the electrostatic force. Well, I know that Tx is equal to the electrostatic force. So you really have a triangle. This side of the triangle is 0.0098 newtons because Cy and mg are equal. You want to know Tx, which is equal to Fe, electric force. And they tell you that this angle here is 30. So this angle here is 30. The tangent of 30 is equal to the electric force divided by 0.0098. So when I did that, I got the electric force to be the tangent of 30 times 0.0098. And that gave me 5.66 times 10 to the minus 3. This newtons for this force. And then part D, as in dog, said, what is the charge? So F is equal to K, Q1, Q2 over R squared. But I know that Q1 equals Q2 because it tells you they're equally charged. So my equation becomes F equals K, Q squared over R squared. So 5.66 times 10 to the minus 3 newtons. Then you multiply by R squared, which is 0.03 meters squared. Then I'm going to divide that by 9 times 10 to the 9th. And that equals Q squared, but I just want Q, so I take the square root of that stuff and get Q. And when I did the math, I got Q to be 2.38 times 10 to the minus 8 Coulomb. All right, so that took care of number 9. You could see something like that on the test. Take a look at it. Number 10. The figure below shows 3-point charges that lie along the x-axis. Determine the magnitude and direction of the net electrostatic force on Q1. Q1 is in the middle. So I have Q2 on the left. Q1 is in the middle, as I said. And Q3 is on the right. Q1 is a negative 4 microcoulomb. Q1 is a positive 6 microcoulomb. And Q3 is a negative 7 microcoulomb. They want to know the net force on this little vessel here. Well, it looks like to me that 2 would be pulling 1 to the left. 7 would be pulling 1 to the right. So I'm going to have to subtract those because they're in opposite directions. I want the force of 2 on 1. So that's K. Times Q2 times Q1 for their separation. And it tells me 0.20 meters. That's a bit square. So the force of 2 on 1 is equal to, I got 5.4 newtons. And then I had to find the force of 3 on 1. So 9 times 10 to the 9th again. And Q3 was 7 times 10 to the minus 7.0 is what I should have written. Times 10 to the minus 6 coulombs times 6.0 10 to the minus 6 coulombs, all over 0.15 meters. Don't forget to square it. So the force of 3 on 1. When I got that, I got 16.8 newtons. that direction, that direction. So F next, my negative force and my positive force. My positive force is 16.8 newtons because it's to the right. And then I have a plus and negative 5.4 newtons to the left, so I got 11.4 newtons, and it's to the right. Okay, number 11. Number 11 is a right triangle. I have a charge here, a charge here, and a charge here. I know that these two sides are 3 meters, I think it is. Yeah, so that's a 45, 45, 90 triangle. So this R here is going to be what? It's 32 times 3 or something like that, so we can figure that out. Determine the magnitude and direction of the net force on Q1. So this is Q1 here. This one is Q2 down here. And Q3 up here. So I need to find the force, so I have 3 on 1. That's a K. Sorry. Times Q1. Well, Q1 was 4.5 times 10 to the minus 5. Coulomb. Q3 was 1.8 times 10 to the minus 5. They're both positive. And then the distance R, I got 4.24. Pythagorean theorem, don't forget to square it. So that one is 0.405 newtons. And it's pushing along that diagonal, which we'll have to deal with in a minute. The force of 2 on 1 is very similar. 9 times 10 to the 9. 4.5 times 10 to the minus 5. And Q2 is 1.2 times 10 to the minus 5. And they're separated by 3 meters. Don't forget to square it. And so when I did that math, I got 0.54. And 2 is pulling 1 to the left. And then I said, well, this one really has an X component and a Y component. And so I made my XY chart. And I used sines and cosines. And if you don't remember how to do that, you might want to go back over it. So I said the cosine of 45 degrees times 0.405. And then I said the sine of 45 degrees times 0.405. And then this one was negative x, so I said 0.54. And I made it negative because it was to the left. And when I added my x's and y's up, I got negative 0.254 for the x's and a negative 0.286 newtons for the y's. I'm going to do Pythagorean theorem, and I'm running out of time, so I'm going to do this one fast. So when I did Pythagorean theorem, I got 0.382 newtons. And then I found theta. And I got theta to be 48.4 degrees south of west, because I had a negative x. And then negative y. And here is my theta. Now I did this tangent and figured it out. I'm going to stop this, and then I'm going to post it on YouTube. I'll talk to you later.